A logical question, after you've dropped a few AFM probes on the floor, is why are they so small? The chips, the rectangles I've sketched here, they're a few millimeters in size, and the cantilevers you can barely see. To answer that question, I have to go through and talk about cantilever spring constants. So here's a cantilever and a tip viewed on the side, and if a force is applied to it, it bends. And let's get a force in here, right? And if we consider just a very small element of that cantilever, in the upper part, the atoms are squished together, and in the bottom part, they're being pulled apart. So that generates a torque that counters the applied force. And if you remember from physics, for equilibrium, the sum of the forces must equal 0, and the sum of the torques must equal 0. So and a torque is a position vector crossed with a force. And that position vector runs from a particular volume element along the length of the cantilever. So that's our R, and that's our F. What you do to find the spring constant is to integrate along the length of the cantilever, considering one volume element of the cantilever at a time for the force acting on the tip, which generates the torque, and the counter torque is built up by the deflection of the cantilever. After all that, what you end up with is that the spring constant in the direction normal to the surface of the sample is equal to the elastic modulus times the width of the sample of the cantilever times the cube of the thickness of the cantilever divided by 4 times the length of the cantilever cubed. This is for a rectangular cross-section of a cantilever, the ones that looked like diving boards. Repeating that equation on this slide, we want the spring constant in the normal direction to be small, because that way we can control our force, keep our force small, so as to limit the pressure between the tip and the sample. It's the pressure that causes damage. The elastic modulus, that's controlled by the fact that these are made in the same facilities that are used to make computer chips, and there are very few materials that are compatible with those processes. They are silicon and silicon nitride. As far as the width is concerned, we will have a cantilever like this, and we're bouncing a laser beam off the back of the cantilever, and you position your laser beam along the length near the end, and that laser beam has a width, and it's difficult to get that width less than 10 microns. So the widths of our cantilevers are on the order of 30 to 40 microns. The thickness is on the order of, a half to 2 microns. And then the length is on the order of 100 to 400 microns. So if you look at the equation again, you see that the thickness is cubed, and the thickness is very small. So indeed the numerator is much smaller than the denominator. And in order to achieve such small thicknesses, you need to have this silicon microfabrication process. If you tried to make a cantilever yourself, well, I've never seen one that matches the low spring constants that you can make with a silicon microfabrication facility. For completeness, I should tell you about the spring constant for the direction parallel to the surface, and that is the elastic modulus times the width cubed times the thickness divided by 4 times the length cubed. And because the width is so much bigger than the thickness, and you cube it, this spring constant in the direction parallel to the sample surface, that is a really big number. And that's good because when we bounce our laser beam off the back of the cantilever, we're not sensitive to those motions. And then, what about the spring constant when you apply a force to the tip that, instead of being perpendicular to the sample surface, is parallel to the sample surface and perpendicular to the long axis of the cantilever? This would be what happens in lateral force microscopy. Well, you get the shear modulus times the width times the thickness cubed divided by 3 times the length times the height of that tip. I'm going to use eta because I use h for other things. And that can range from 5 to 20 microns. Eta squared. Let's say you wanted a cantilever for an experiment that was very stiff in the lateral or the torsional direction, resistant to friction, but very compliant in the normal direction, so very low spring constant. What you can do to figure out which one to purchase, or perhaps you're a designer of cantilevers, is to divide one spring constant by the other and then look at what that tells you. So here are those two expressions for the torsional and normal spring constants. We see a lot of cancellations for the width, for the thickness, and one factor of L. And so we simplify this down to 4 shear modulus over 3 times the elastic modulus. That's controlled by the selection of materials, silicon or silicon nitride typically. And then we have the length over the tip height squared. Okay, so that means if you were looking for a cantilever that was stiff torsionally and compliant normally, you would want one that is long and yet has a short tip. And then you can do similar kinds of calculations for other experiments that you're considering. Another thing that we should consider as we're talking about cantilever size and selection is the resonant frequency. I've said before that the resonant frequency is equal to the square root of the spring constant over the mass. And you would think that the mass would just be equal to the density times the volume of this rectangular cantilever, that being the width, the thickness, length. But it turns out that's not quite true. Think about the cantilever and how the mass of the cantilever is uniformly distributed along the length. One end of the cantilever moves, but the other end is fixed. So it turns out that we use an effective mass, which is a fraction of what you would instinctively think would be the answer. It's 33 over 140 of the density times the volume. Now we can go and solve for the resonant frequency. We will have the expression for the spring constant, and I'm doing the normal direction. Elastic modulus width thickness cubed over 4L cubed, and now the effective mass is in the denominator, but that 140 we can put up in the numerator. And here we have the density times the volume again. There's some nice cancellations. 4 goes into 140 35 times. We have a cancellation of 1 power of thickness. The width goes away completely. And so we will end up with 35 elastic modulus over 33 density square root, and we can take the t out of the square root as well as the L. Okay, so this means that after you've made your selection of materials, which determines your modulus over density, then if you want a high resonant frequency, you would want a thicker cantilever that is short. And because we want the cantilever to have a resonant frequency at least in the kilohertz range, so as to be very different from building vibrations, this is why cantilevers are so small. Here are the two important equations in this lesson, that of the spring constant in the normal direction and the resonant frequency of that spring constant. In selecting a cantilever for the spring constant, you would be thinking about range and resolution. So if you want to apply a large range of forces, then you need a bigger spring constant. If you want good force resolution, you would want a smaller spring constant. As far as the resonant frequencies go, they should be at least a few kilohertz in order to be above the building vibrations. But if you're using an oscillatory mode, you would want a dynamic mode, non-contact or intermittent contact. You would want a still higher resonant frequency, at least a few hundred kilohertz. The reason for that is that the lock-in amplifier in the feedback loop for the dynamic mode, it needs a few cycles of oscillations in order to give an output signal. The longer the period of oscillation, i.e. the lower the frequency, the longer you have to wait. So by having a cantilever with a higher resonant frequency, you can get your data faster. Note that in some sense these two equations are diametrically opposed. For the spring constant, we generally want that small. For the resonant frequency, we generally want that big. And yet in each case, the thickness is in the numerator and the length is in the denominator. And so when you're optimizing one, you're compromising the other. Fortunately, there's a wide variety of cantilevers on the market, and there's probably one that matches your needs.